Hello, this is Nicholas Vinen from Silicon Chip Publications, and today I'd like to talk to you about two shortwave radio receiver projects, one of which we published previously in the magazine recently, June and July 2025, and one of which is about to be published in the April 2026 issue. So this is the earlier design that we published. It's a SSB, a single sideband, so it's a shortwave radio that can pick up either the lower sideband or upper sideband transmissions. And the advantage of those is they take up half the bandwidth of a regular AM transmission. And here we have some theory about different ways to decode USB and LSB transmissions, single sideband transmissions. And he talks about various approaches he tried, some of which sound good in theory but don't work so well, at least not without a very complicated circuit, some circuits that he tested. And here's some more information about amplitude modulation, upper sideband, lower sideband. Here's the radio that he designed. Well, this is part of it. It's two boards. This is the control board that has this LCD screen, Arduino Nano oscillator that generates the tuning signal. Here's the circuit for the control board. It's pretty straightforward. And then here's the radio board, the RF board. So it has a series of switch capacitors and some switch transformers to tune the antenna to a rough range. And then it has a variable capacitance diode here that it uses for fine tuning. And then there's a dual gate MOSFET that's used as a gain stage, and then a mixer, another dual gate MOSFET, a crystal filter, another dual gate MOSFET, another mixer, and then that's fed to the control board for audio demodulation and so on, and ultimately to go to a speaker. There's the RF board. You can see it's reasonably complicated, and it has this fairly elaborate crystal filter module with 6 crystals on it and a bunch of capacitors. Anyway, it works well. It's a good design, but it's, as you can see, it's relatively complicated. It's a pretty traditional analog design. And then we published the second part in the July issue. This has the construction information here, the control board PCB diagrams, the RF board PCB overlay diagrams, some photos, drilling details. So it's a pretty straightforward radio, pretty traditional design. So that was last year, mid-2025. Now in April 2026, we're about to publish this new design from the same author. And again, it's a shortwave receiver, but this one is a software-defined radio. That's what SDR stands for. So in other words, some of the signal processing, instead of being done in analog, is done digitally, and that simplifies the circuit. So here's the RF board, and if you compare it to the original one here, you can see that it's quite a bit simpler. It still has the same arrangement with the switch transformers, switch capacitors for broad tuning, and the variable capacitance diode for fine tuning. So that bit's pretty much the same. And then there's an RF gain stage like before, but this time, instead of all the other mixers and gain stages, he has this 74CBTLV 3253 dual 1/4 multiplexer. Now, by the way, Charles points out he didn't originate this idea. It comes from someone called John Dawson. So he's using John Dawson's software, but he's designed the hardware around it. So what happens is there are control signals from the control board here, these LOI and LOQ signals that go to the control terminals on this multiplexer, and they switch the either incoming RF or ground to one of 4 places. So basically, the 4 places are the inverting and non-inverting inputs of these dual op amps. And there are some capacitors and resistors there, so this forms some sort of a differential amplifier with time constants. The idea being, if you rapidly switch the signals between these different points in the correct sequence, it will actually extract the I and Q signals, which are basically a vector related to the phase and the amplitude of the signal that's being tuned here. So it's kind of a digital mixer in a sense, and it's driven by the digital circuitry, by square waves on these pins. The result is analog voltages, RXI and RXQ, which contain the information needed to actually decode the radio transmission. They're slowly changing analog voltages, so they get fed back to the control board to be sampled by the analog to digital converter on the digital module. So the software provides these square waves, gets these 2 voltages, and from that it's able to decode the audio signal that was modulated, including various different modes like AM, upper sideband, lower sideband, so on. If we continue here now, we can see This is the control board. The front has some potentiometers, rotary encoder, OLED screen. On the back is a Raspberry Pi Pico module, and that's what does all of the software-defined radio jobs and interface. And then you can see here the RF board is a lot smaller and simpler than the one. If we compare it back to the original list, there's the RF board. You can see it's a much larger board. So this section here on the left is basically the same, but then there's not much more on this board because it's basically just the single RF gain stage and then going into the multiplexer and then feeding to this header. So here's the circuit for the control board. Again, it's pretty straightforward. It's just the microcontroller module with some things connected to it, an audio amplifier, a screen, clock generator, which is not actually required because the Pico is able to generate these clock signals itself. So that's a pretty, the part of the Pico module only costs about $10. It's a pretty powerful device with a dual core chip, and it's pretty amazing, really. It can do all of this job of synthesizing the oscillator and analog to digital conversion and the demodulation and decoding all in the software on that. And then if we have a look here, there's the control board overlay, RF board overlay. There obviously are some surface mount parts there, but it's all pretty straightforward. And the parts list is considerably smaller, and the software can even drive an external LCD screen, which is nice. You can see here there's a waterfall and spectrum display that you can get. So there's the radio on operation. Yeah, the OLED has a signal level indicator, and you can also use it to see what frequency is tuned and so on. And it's a straightforward radio to operate. There's basically tuning, volume, gain. That's pretty much it, and on off. So a neat little design there, enabled by some very clever software running on the Raspberry Pi, and the result is quite a bit simpler and cheaper device to build that has more capabilities. So I think that's a pretty comprehensive little shortwave receiver. Now, this software, I believe, would work on the AM broadcast band, but this design doesn't have the ability to tune into it. So you can see here that it has 7 bands that are provided by switching those capacitors, and basically they cover 3 to 30 megahertz. So it's the shortwave band in various steps. If the front end was modified to be able to tune down to 576 to 1800 kilohertz or so, then you could tune in broadcast band AM stations as well. Anyway, he's obviously just decided to keep it simple, not try to make the front end cover such a wide range, but it would be something that you could potentially do. And of course, if you're interested in the software, we have links to John Dawson's software that you can not only use to run the radio, but also see how it works. And he has quite a bit of information on his website about how this design works, and this, including this quadrature sampling detector feature. So that's coming up in the April 2026 issue, on sale late March 2026. And that's all the information you need to build it. We can supply the circuit boards and a few of the parts, but you'd have to gather most of the parts. They're all pretty straightforward, and we've given sources for anything that's not obvious. So thanks for listening. I hope you enjoy the magazine.